I am Aniket Koul, and today we'll be discussing the 31st problem of the CP-31 sheet by TLE Eliminators under the 1200 questions. So I'll be moving to the CP-31 sheet, and we can see that the 1200 parameter has been checked. I would be moving to the 31st question, that is rock and lever. So let's begin. Danik urgently needs rock and lever. Obviously, the easiest way to get these things is to ask Hermit Lizard for them. Hermit Lizard agreed to give Danik the liver, but to get a stone, Danik needs to solve the following task. You are given a positive integer n and an array A of positive integers. The task is to calculate the number of such pairs I, j such that I is less than j and ai bitwise and with aj is greater than equal to ai bitwise or with aj, where and in this represent the bitwise and bitwise or respectively. Danik has solved this task, but can you solve it? So the input format and the constraints are as follows. The first line of each test file would contain a single integer t denoting the number of test cases, and t can go up till 10. And then first line of each test case would represent one single positive integer that can go to 10 power 5, representing the length of the array. And then the second line of each test case would contain n positive integers ai, where each ai can go from 1 till 10 power 9, and these represent the elements of the array. Now it is guaranteed that the sum of n overall test cases does not exceed 10 power 5. Now you have to output for every test case a single non-negative integer denoting the answer to the problem. Now as you've read the problem statement, we can move on to discuss it. So for every test case, we are given two things, that is n and a. So n is an integer which denotes the size and denotes the size of our array A. So our array A is of size n. Now we are asked to find the number of pairs I, j such that I is less than j and they lie between 1 and n. Also, ai bitwise and with aj is greater than equal to ai bitwise or with aj. So we have to count the number of pairs for which this property holds true given this condition, and we have to output that single integer as our answer. Now let's move on to understand the sample cases. So let's take this one. Let's paste it here and remove any extra part. Also, let's increase the font size. Great. So now what we can do is, this is n and this is our array A. If I write my array here 1 4 3 7 10, we could see that only the indices, so I'll mention the indices 1 2 3 4 5. So only the pair 2 comma 4, so this is the I comma j pair representing the values 4 comma 7 satisfies this condition. So if we see 4 bitwise and with 7, that would be equal to 111, and bitwise and with 100, that would be 100. It's 4, and the bitwise XOR 4 XOR 7, so 111 100, and it would be 1 1 and 0, so this would be 3. So the bitwise AND is 4, but the bitwise OR is 3. So yes, this is a valid pair, but you can see for yourself and you can calculate for all other pairs this property of AI and bitwise AND with AJ greater than equal to AI bitwise OR with AJ does not satisfy. So the answer here would be 1, depicted here as well. So the answer is 1. Now let's discuss the exploit time complexity. So we are given that sum of n overall test cases is less than equal to 10 power 5. Let's check that. Yes, indeed it is 10 power 5. So as there is a bound over sum of n overall test cases, so instead of writing a time complexity as O of t into some function of n, I can simply write it as O of f of n, because n has a bound overall sum over sum of all test cases. So I don't need to include t. So now we also know that in 1 second on Codeforces, we can run about 10 power 8 elementary operations. So that would be our number of operation limits. So now if I run an algorithm in O of n time complexity, that would take around 10 power 5 computations or operations. O of n log to the base 2 of n would take around 10 power 5 into 20, because log to the base 2 of 10 power 5 is approximately 20, and this would give me 2 into 10 power 6, and O of n square would land somewhere around 10 power 10 operations. So as our limit is 10 power 8, 10 power 5 is completely fine, 2 into 10 power 6 is also fine, but 10 power 10 will not come under the given bounds. So again, I want an algorithm which runs around the complexity of O of n or O of n log n. Right. So as we discussed the exploit time complexity, we can move on to discussing the solution. Before discussing the solution, let's make clear what the bitwise and the bitwise OR operations are, so that we can move further quite easily. The bitwise AND operation is quite simple. So what we do, we write the numbers in binary format. So let's say the number is 10110, and the second number is 11011. So what happens is, for every bit position, we see that if both the bits are 1, then their bitwise AND is 1, or in any other case it is 0. So 1 and 0 is 0, 1 0 and 1 is also 0, and 0 and 0 is also 0. So only 1 and 1 is 1, rest all are 0. So this gives me the value 0 1 0 0 1. Right. Now bitwise OR, let's say bitwise OR for the same pair of numbers. So again, write those numbers in binary format, and for each bit position, if the bits are different, so either it should be 1s or 0 or 0s or 1, only then the resultant value is 1. Otherwise, if both the bits are same, then the value comes out to be 0. This is how XOR works. So here the value would be 1 0 1 1 0. This is how the bitwise and the bitwise XOR work. So now let's move on to the actual solution. So the main idea of the solution lies around the condition that AI bitwise AND with AJ should be greater than equal to AI bitwise OR with AJ. Right. Now let's understand the properties of bitwise AND bitwise OR to understand in what cases will this condition hold true. Right. Now, as discussed earlier, that bitwise AND gives the value 1 only if both the bits are 1 at that position, and bitwise OR gives the value 1 only if both the bits at that position are different. So let's use that property to our advantage to actually find out the case where this condition, this given condition would hold true. So before that, we also need to know another condition or another property of numbers represented in binary format. So let's say I am reading two numbers. Let's say this is B1 and B2. Both numbers are written in base 2, and I'm reading both of those numbers from left to right. Okay. Now let's say for some prefix, both of those numbers were equal. So let's say this was 1101, this was 1101. Now at the first position where they differ. So let's say this was 0 and this was 1. If this is the first position that they differ, then the number with 1 at that position will always be greater. This is another property of binary numbers. And this is property of any numbers in general. This also follows for decimal numbers as well. So if two numbers have the same prefix, and if at the first position that they differ, the number with the higher value at that position is greater, right? So this number will be greater, and this is true for binary values as well, right? So let's say if the value was 110 10111, and this value was 11011 000, no matter that these three values are 1 and these three values are 0, but because at the first position that they differed, this value had a 1 and this had a 0, this means b2 would be greater than b1, and we don't need to consider the next values. This is when we are going from left to right. So now, keeping these two properties in mind, let's try to come up with a algorithm, right? So if I have two numbers, a of I and a of j, right? And I write both of them in base 2. So I've written this number in base 2, I've written this number in base 2. Okay. Now I try to find the maximum or maximal set bit in this number, and also I try to find the maximal set bit in this number. Okay. So what is the maximal set bit? So that is the first bit that is set to 1 when I read the number in binary from left to right. So if I go from left to right in a binary number, and the first bit that I encounter, which is equal to 1, that is the maximal set bit of that number, and also known as MSB, right? So what I do is I compare the positions of the MSBs. So usually in binary numbers, what we do is we start indexing the numbers from right to left. So let's say if I write 13 in binary, so that would be equal to 8 and then 4, 12, and then 2, 1. So this is 13. So what we do usually in binary numbers, we index it from right to left. So this is the 0th bit, this is the first bit, this is the second bit, this is the third bit, right? So even if I write 13 as a 32-bit number, so these 29 bits, I think, would be 0. 30th bit is 1. Okay, this is 28. 29th bit is 1. 30th bit is 1. 31st bit is 0. And 32nd bit is 1. Right. So this is 13 when I write it as a 32-bit integer. And why I'm discussing 32-bit integers? Because in C++, inside memory, int is stored as a 32-bit integer, right? So that's why I'm discussing 32 bits. Let's say I also represent 12, right? So 12 again would be 28 zeros in the front, and it would be 1100. Great. So again, if I mention the indices 0, 1, 2, 3, so on till 31st, the leftmost bit will be 31st bit. And same goes here, 3, 2, 1, 0. Now what I do is, let's say this is a of I, and let's say this was a of j. I compare the positions of the MSB, right? So the MSB for a of I is present at the third index, right? And the MSB for a of j is also present at the third index, right? So if the position of MSB of a of I is same as the position of the MSB of a of j, then what would happen? Let's check. Now if I do a of I bitwise and a of j, then obviously the bitwise and of these two bits would be 1, right? Let's forget what would be the bitwise AND here. That is not necessary, and we'll prove why it's not necessary. So here at the third index, I would have a 1. Obviously, all the indices before it would be 0 in both the bitwise and bitwise OR, because each one of them is 0. So there are a few zeros, exactly 28, and this is 1. And I don't need to consider what is here, right? Let's forget it for a second. What would be A of I XOR A of j? It would be 28 zeros right in the front. But what would be the value at the third index? Let's check that. Because both of the bits are equal to 1, the XOR would be 0, right? XOR is 0. And again, I don't want to consider what is here. Let's leave it for a second. But here I see that for AI and AJ, also for AI XOR AJ, this prefix is same, the 28 zeros, this prefix is same. And this is the first bit where they differ, right? And at the first bit where they differ, AI bitwise and AJ has a 1 there. So can I say from my earlier theorems that AI bitwise and AJ would be greater than equal to AI XOR AJ? Can I say that? Actually, this would be a greater than, but again, it would satisfy the inequality, right? If it is greater than, it is also greater than equal to. So is it true? Yes, it is. So I have devised an algorithm where I can say that if I compare the positions of the MSBs, the maximal set bits of A of I and A of j, and if they are equal, then always A of I bitwise and with A of j would be greater than equal to A of I bitwise and with A of j, bitwise or with A of j, right? But let's take a condition where MSB of A of I, position of MSB of A of I is not equal to the position of the maximal set bit of A of j. Then what happens? Let's check. Let's say A of I was 13. Let's keep that same. And A of j was 7. Right. So if I write 13 as a 32-bit binary number, so it would have 28 zeros in the front. Then it would have a 1, 1, 0, 1. And 7 would have 28 zeros in the front, and it would have a 0 again, and then 1, 1, 1. So this is 7, and this is 7, and this is 13 in 32-bit representation. Now let's again index them from right to left, 0, 1, 2, 3, so on till 31, and again 0, 1, 2, 3, so on till 31. Now we can see the position of the maximum set bit for A of I is 3, and the maximum set bit position for A of j is 2, right? So it satisfies the condition that position of MSB of A of I is not equal to the position of MSB of A of j. So what happens now? AI and AJ, bitwise and AJ, is 28 zeros in the front, right? Now at the third index, it is 1 and 0. So obviously bitwise and is 0. And now let's leave it for a second. What are the rest of the values? I don't need to care as of now. Let's also calculate A of I bitwise XOR with A of j. Again, it would be 28 bits in the front with zeros. But here on the third index, one value is 1, other value is 0. So the bitwise XOR would be 1. And let's again not consider what values are there behind it. But we know at the third index, we have a 0 for the bitwise and a 1 for the bitwise XOR. Also, we can see now that for the first 28 bit positions from left to right, they both are the same. So the first position where these two numbers differ is the third index, right? And for the third index, there is a 1 for the bitwise XOR and there is a 0 for the bitwise AND. So again, I can say that A of I XOR A of j would be greater than equal to A of I bitwise AND A of j, right, from earlier theorems. But this is exactly opposite of what we require. We required this, right, that bitwise AND should be greater than equal to XOR. But here we are saying that XOR is greater than equal to AND. So we can prove that whenever maximal set bit position of A of I is not equal to the maximal set bit position of A of j, then this condition, which is also mentioned in the problem statement, does not hold true. So finally, we can state our algorithm as follows. Let's calculate the maximal set bit for every element in my array A, right? Let's say for A of 0, it is 3, A of 1, it is 2, A of 2, it is 3, A of 3, it is 4, and A of 4, it is also 4. So now I want to calculate the number of pairs, right? So what can I say is A of 0 has 3, A of 2 has 3, so this is one pair. A of 3 has 4, A of 4 is 4, so this is one pair. And let's say A of 5 was also 3. So what would happen now? So A of 0 and A of 5, 0 comma 5 is one pair, 1 comma 5 is one pair, and 0 comma 1 was already one pair, right? And this is only for 3. And let's say if A of 6 was also a 3, then what would happen? Then 0 comma 6 would also be a pair, 1 comma 6 would also be a pair, and 5 comma 6 would also be a pair. So if there were only 2 threes, then I would have one pair. If there were 3 threes, I would have 3 pairs. And if there were 4 threes, there were 6 pairs. So can you come up with a formula? Does it look something similar? Doesn't it look like NC2? This n is not the size of the array. So let me define it with a different variable. So let me restate it. Doesn't it look like XC2, right? Number of ways to choose two elements from a set of X elements, right? Because let's say if I had X number of threes and I had to choose exactly two of them, right? So the number of ways to choose them would be XC2, and that would also be the number of pairs for which the MSB would be 3. The position of MSB would be 3. And now I repeat this for every value. So I repeated this for 3. Let's say I got 6. I repeat this for 2. So there is only one 2. So for it will be 0. 3 was already calculated. 4, for 4 there were two 4s. So the answer would be 1. So total number of I comma j pairs would be 7. So this is my final work. And now let's calculate the time complexity of this approach, right? Now the first part of the algorithm is to calculate the position of my maximal set bit, right? And how do I calculate that? What I can do is I can run a simple for loop for I goes from 30 to 0, right? And what I can do is simply calculate the, so I should not name it I can name it j, right? So for every a of I would calculate a of I bitwise and with one left shift j times. So what does this represent? This is basically 2 power j. So if I bitwise AND of a of I with 2 power j, this will return a non-zero value. So this value will be greater than 0 only if the jth bit from the right, if the jth bit from the right is set, and if it's unset, it returns 0. So for the first j, when I move from 30 to 0, for the first j for which it returns a greater than 0 value, that j is itself the position of the maximal set bit. So that means for every number, I had to run a loop of 30, right? Now, You can consider this time complexity as to be O of n into 30 or O of n, or you can also consider it to be O of n into log base 2 of maximum AI, right? These both of them are correct, and these both of them are exactly the same value. It's up to you what you consider. Because you already know the max of AI can only be 10 power 9, so I just run a loop of 30, so it becomes O of n, because this is again a constant value. And for the part where I want to calculate the number of pairs using NC2, NC2 is XC2 can also be written as x into x minus 1 by 2, and this value can be calculated in O of 1 time, given we maintain a map or a frequency array kind of thing, where let's say f of I represents number of values which had ith position as its MSB, right? So if I maintain an array, what array size should be? It should be 31, right? Because the MSB position can be from 0 to 30. Why I am saying only 30? Because 2 power 30 is the first power of 2 which is greater than equal to 10 power 9. So I need to check only till 30 bits. So I'll make f of size 30, initialize is 0, and then f of I would represent the number of values in my array A which have the ith bit as its MSB. And finally, then for each I in f, I would add f of I into f of I minus 1 by 2 into my answer, and keep doing it for every f of I, and at last return the answer. So this is again an O of 30 loop, or you can say an O of 1 loop. So my total time complexity again comes out to be O of n, or O of n into log base 2 of maximal AI, and it is up to you how you interpret it. So now let's move on to the implementation. So we take an input for the number of test cases, then for each test case I take an input for the size of the array, and then I input the array itself. So again, this operation is O of n, and this max set bit is the same array that I referred to as f in my explanation, right? So max set bit of I stores the number of values in my vector v or the array A which have the ith bit as its MSB. So again, how do I check that? I run a loop from 30 to 0, and then I calculate the value of v of I bitwise and with one left shift these many times, bit number of times. And again, as I said, this value is same as a of I bitwise and with 2 power bit. So it returns non-zero value only if the bit position, or if I replace bit with j, so it is better understood, only if jth position is set in a of I. So this is a very nice way to check if the ith position is set or the jth position set is a of I or not. And as we are running this loop from 30 to 0, it is basically checking the bits from left to right instead of right to left, and hence the first bit for which this value is non-zero is the MSB. So then I increment the value of max set bit of bit, and then I break. So as I said, this value is O of n, or you can also write it as O of n into log of maximum of a of I, as you wish. And then again, this is simply an O of 30 loop, or you can also write it as an O of 1 loop, because O of 30 is constant, where I'm just adding max set bit of I into max set bit of I minus 1 by 2, which is same as if I refer to my explanation, f of I into f of I minus 1 by 2, and this will tell me the number of pairs such that both the values in that pair have the f of ith bit as its MSB. And now I just return my answer. So finally, the total time complexity would be O of n, or you can also write it as O of n into max of log of max value, and the total space complexity would be O of n also, because we're just storing an array, and we are storing another array which is but of constant size, that is 31. So space complexity would be O of n nevertheless. And finally, for the ending remarks, I would say the problem was quite interesting because it utilized various number theory concepts like maximal set bit, and when bitwise AND is greater than bitwise OR, and when it is lesser, and then finally combinatorics to calculate the number of pairs. So it was a nice mashup of uh, topics as always. So I hope you liked the problem. Thank you.